Okay guys, this is take 7 on this video because I've had so much trouble trying to get it done. So hopefully 7 is the magic number. We're on page 521, lesson 88. This is exponential functions, exponential growth, and exponential decay. Unfortunately, we are in a state where we have an example of an exponential growth right now with the number of corona cases. Eventually that will level off and it will begin to decrease exponentially, just like it increased exponentially. Prior to now, I always used a different example, which was a little bit happier example, and it was the number of Starbucks cafes. When they first started coming out, they increased exponentially. So, I mean, everybody knew it wasn't going to last forever, but it did increase like this until the late 80s or early 90s, where they reached their plateau and ended up having to close some stores, like one that we had here in Roswell up by Walmart closed, and many other ones did as well. But it was an example that a lot of statistics classes and business math and business calculus classes used as a classic example of exponential growth. All right, so we did work with this last year at the very end of Algebra 2. The equation that we use is A sub t, that means the amount after a period of time, is equal to A naught, which is the initial amount, what we start with, times E raised to the kt. E is that constant, I think it's like 2.7818. If you, on your calculator, raise E to the first power, it'll tell you exactly what E is. And then this is a constant that changes with every problem. And this is the time that elapses between the initial amount and the time that the amount after a period of time. All right, so in the first example here, it says the number of bacteria present at noon was 400. So that's our initial amount. And 9 hours later, the bacteria numbered 800. Let's hope that this is a good bacteria and not a bad bacteria. Okay, so the K we don't know, but that happened 9 hours later. So there's how we plug in based on this problem. So you can see the only variable that we have is K, because remember, E is a constant. It's a number. Okay, it's just like pi. It's always the same number. So first of all, we're going to divide both sides by 400. So we get 2 is equal to E to the 9K. And hopefully by now you remember that when we have an E in a problem, to undo that E, we take the natural log of both sides. So we have ln of 2 equals ln of E to the 9K. Well, what happens to the ln and the E? They cancel. So we have ln of 2 equals 9K. So to get K by itself, we just divide both sides by 9. So there's our K. And from that, we can actually get the exponential equation that we could use to find basically any unknown in this problem. And what I mean by that is it would be A sub t equals, 400 is always our initial amount. That's not going to change. E, now we know that K is ln of 2 divided by 9 t. So that's called the exponential equation for this problem. Sometimes they'll ask you to give the exponential equation. In this particular problem, they don't, but I know that it does happen in some of the problems in the homework and then on the test. So be aware, if it asks you to write the exponential equation, this is it right here. Okay, another thing it may ask you to do is to sketch the curve. It's a super simple sketch. The initial amount was 400, so we mark 400 here. It's increasing, so it's going to be an exponential increase. So there's the sketch. That's all there is to it. Nothing fancier than that. Okay, now then, to finish this problem, it says, assume exponential growth and find the number of bacteria present at noon the next day. Well, we started at noon on one day, and now it's asking us for noon the next day. So how many hours elapsed from noon yesterday to noon today? Right, 24. So plug that in for t. So a sub t will be equal to 400 e to the ln of 2 over 9 times 24. I'm going to go ahead and put this all in parentheses so that you realize that's what you have to put in the calculator. And I'm going to show you what it looks like in the calculator. So, okay, so here I'm just going to put this up here. All right, so you can see that I typed in 400. I had to hit second ln to get this. Second ln to get this. And then you just put this in, this in for the exponent. So you notice I put in ln of 2, close the parentheses because that's all I'm taking the natural log of is 2, divided by 9, and then that whole thing times 24. Okay, then hit enter and you'll get this for the answer. So AT is equal to 2539.84. And if you notice, that's just a little bit different than what they have on page 522. It's because they took and put this in the calculator right here and got a decimal value of only 3 places for that, which is not very accurate at all. And they continued to round through the whole problem. We did not round until the very end. So whose answer is more accurate? The book's or ours? Like usual, ours is more accurate. So this is the way I want you to do it. Okay, bottom of page 522. The number of bacteria present when the experiment began was 1,200. So that goes here. After 100 hours, there were 2,700 bacteria present. So now there's 2,700, and that was after 100 hours. Okay, so before we even read the rest of it, first of all, it does ask for a sketch, so I'm going to come down here, put my little sketch. I can tell it's increasing without reading that into the problem because it starts at 1,200 and it goes to 1,200. That's getting bigger. So here I'll put 1,200. And it's increasing. So there's my sketch. Don't forget, it's that simple. Okay, now let's go ahead and solve for k. So we're going to divide by 1,200 on both sides. So the zeros cancel, 3 goes in there, 9, and then there 4. E to the 100k. And then how do we get rid of the e? We take the natural log of both sides. So natural log 9 over 4 equals natural log e to the 100k. That cancels. So I have 100k equals ln of 9 over 4. And then to get k by itself, we divide both sides by 100. So there's our constant. And that's an exact value, and I'm not going to round it off. All right, so now it says, assume exponential growth and find the time required for the number of bacteria to increase to 30,000. All right, so now I want the amount to be 30,000. The initial amount was 1,200. E to this thing right here, ln 9 over 4 divided by 100, t. We're solving for t this time. They give us everything else. And by the way, I should have written the exponential equation. And we just plugged into this for the amount after a period of time. All right, so similar to how we solved for k, we're going to divide both sides by 1,200. And let's see, that's 50 over 2, which is 25, equals e to the ln of 9/4 divided by 100 t. Okay, now this e and this ln don't cancel. all right? Because that's not the only thing that's in that exponent. It's not the ln of everything up there, okay? So don't make that mistake. So in order to get rid of this e, I have to take the natural log of both sides again. So I get ln of 25 equals ln of this. So these cancel, and what I actually have is ln of 25 equals ln of 9/4 over 100 times t. So you can see there, we need to get t by itself, which means we're going to multiply by the reciprocal of this guy. So times 100 over ln of 9/4, and over here times 100 over ln of 9/4. Okay, so these cancel, and we're going to get t equals. And let me do this in the calculator real quick and take a picture of it and show it to you. If you have your calculators, I'll walk you through it. I'm going to put parentheses ln 25, close the parentheses, close it again, times 100. Actually, I'm going to take that 1 out. Okay, ln times 100, and then that's going to be divided by natural log of 9 divided by 4. Okay. All right. So let me show you what this looks like. The first line is what I entered in the calculator. And the second line is when you hit enter. Okay, I'm going to have to cover something up when I show this to you. Move it up here out of the way. Okay, so you can see that what I did was I typed in ln of 25, which was what this was, times 100 divided by ln of 9/4. You hit enter, and so we get 396.94. That was hours, so it means that it's going to take it 396.94 hours to get to 30,000 bacteria. If we divide that by 60, that's what? 66. No, divide that by 24, that's not that much. Be 12 days that it would take it to get to 30,000. So again, I'm hoping that's a good bacteria. All right, next one, page 523. 88.3 says the amount of substance initially present was 400. Okay. And after 90 hours, only 380 grams remained. 380. It's not decreasing very rapidly if it's only gone down that much after 90 hours. But now there's something else we got to realize here. This one is not increasing. This one is decreasing. Okay, so when I draw my sketch, which it does say to make a sketch, it starts at 400, but it's decreasing, so it's going to come down like this. You'll notice it never gets to 0. Okay, never comes down to 0. It decreases and gets really close to 0, but it won't ever become 0. All right, another thing is if we were getting a decimal approximation for K, it would be negative. Anytime your K is, when your curve is decreasing, then your K is going to be negative. If it's an increasing curve, then the K is going to be positive. All right, and you don't really need to worry about that because we're going to leave it in exact form. But if you were getting a decimal value for it, you'd know that if it came out to be a negative K, it's decreasing. All right, so let's go ahead and solve for K before I even read the rest of the problem. So divide by 400. So that's 19/20 equals e to the 90k. And then to get rid of the e, I'll take the natural log of both sides. So there it cancels. I have ln of 19 over 20 equals 90k. Divide both sides by 90. So there's k. ln of 19 over 20. Notice how I put that in parentheses because I don't want it to get confused. I'm taking the natural log only of 19 over 20 and then dividing that by 90. So let's go ahead and write our equation. A sub t equals, the initial amount was 400, e to the ln of 19 over 20 divided by 90 times t. All right, now I'm ready to go back and look at the rest of the problem. It says, assume an exponential decrease and determine the half-life of the substance. Half-life is really important when you're talking about radioactivity. It's a major concern because radioactivity never goes completely away. We have a low-level radioactive waste site in Carlsbad. It's called the Waste Isolation Pilot Project, or WIP. And it's supposed to only have low-level medical radioactive waste, like from X-ray labs, their lab coats, anything that's in the room where X-rays are taken, that kind of thing. However, there's been talk that they have more in there than that. And most recently, in the last couple weeks, the government is proposing to put a high-level radioactive waste disposal in southeast New Mexico. So this kind of thing is really important to us because we want to know how much of that radioactivity is going to be present for our kids or for our grandkids. It's not something that just goes away. So when it says half-life, if I originally start with 400, it means that I'm going to have how much left? Half of 400 is 200. Now I'm going to write this for this time, but you don't really need to, and I'll show you why. When I divide this by 400 on both sides, which is what we would do, 200 over 400 is what? It's 1/2 for half-life. So when you're finding the half-life, you can really skip this step and just put 0.5 equals e to the ln 19 over 20 divided by 90 times t, because it's asking for the half-life. It'll always come out. When you take this and divide it by, or divide this by this, it will always come out to half if you're finding the half-life. If you feel more comfortable going ahead and plugging this in and solving for it, that's fine with me. I'm just telling you that you don't have to show that step. So now remember, to get rid of this e, again, it won't just cancel. I have to take the natural log of both sides. So ln of 0.5 will be equal to ln of this. So these cancel, and I have ln of 0.5 equals ln of 19 divided by 20 over 90t. So to get t by itself, I'm going to multiply by 90. Let me erase some of this. It's the beauty of using the iPad. By 90 over ln of 19 over 20 on both sides. So times 90 over ln 19 over 20. That cancels, t equals, let's see, do this on the calculator. So I'm going to put ln of 0.5, that, and I'm going to put this all in parentheses, so put one there, parentheses, ln 0.5, close it, times 90, close the parentheses, divided by The natural log of 19 divided by 20. All right, so let me show you again what we get here. Sorry. I'm trying to get better at this, guys, and show you more than what I was doing the first week. Okay. Okay, import the picture. Move it out of the way. All right, so you can see that I put in here the ln of 0.5 right here times 90, and I put that in parentheses because that's the whole numerator. And then I divided it by the natural log of this, and that was also in parentheses. So the answer comes out to be t equals 1216.21. So that means in order for it to get to half, or to get to 200, see what was that, 200 grams of whatever the material was, it's going to take 1216.21 hours just to reduce that much. Okay, one more example. All right, on page 524, 88.4 says, a radioactive substance decays exponentially. Thank goodness it doesn't increase. After 100 years, 500 grams is left. So for us right now, our initial amount is 500. So we're going to start with 500. That's our first amount. And after 200 years, only 300 grams remains. So we started at 100 years, and now 200 years later, there's 300. So how many years elapsed in between? 200 minus 100 is 100. So in this case, we don't know the initial amount. That's one of the things they ask us to find. Find the amount of substance that was initially present and its half-life. All right, so to do any of this, we need the constant. So let's go ahead and find that. So that's 0.6 equals e to the 100k. And by now you get the drift. We're going to take the natural log of both sides. That'll cancel. ln of 0.6 equals 100k. Divide both sides by 100. So there's our constant. Okay, so the equation becomes AT equals, I'm just going to leave A not there because that's not really the initial amount. Okay, so there's the equation. All right? To find the half-life, we could actually do that right now without knowing the initial amount, because no matter what the initial amount, the half-life will be twice that much over here, right? I mean, this would be 400, 200, 500, 250, whatever. When we divide it, we'll get 0.5 equals e to the ln 0.6 divided by 100t. So it doesn't matter what the initial amount was. This would be ln of 0.5 equals ln of e to the ln 0.6 over 100 times t. So that would cancel out. You have ln of 0.5 equals ln of 0.6 over 100 t. So you can see that to get rid of the ln 0.6 over 100, we're going to multiply by the reciprocal on both sides. So it'll be 100 over ln of 0.6 times ln of 0.5 is equal to ln 0.6 over 100t times 100 over ln 0.6. You see that that cancels, and we'll get t equals, okay, let's do that. That'll be ln 0.5 times 100 And then that's going to be divided by ln of 0.6. All right, let me take a picture of that. And put that right here. So the answer we get there is the half-life is 135.69, and that was years. So 135.69 years to get down to half of what we start with. Now the other part we need is to find out what the initial amount was. So we're going to go back to this equation right here. And we know that there was 500 present after 100 years. It said 100, after 100 years, 500 grams was present. So this will be the K, which is ln 0.6 over 100, and that's going to be times 100. Okay, so now we're going to take and this thing keeps going sideways. All right, so we need to get A naught by itself, but I need to get rid of the E. So if I take the natural log of both sides, looking here to see 500 let me just put it in the calculator and then I can show you. That should cancel, so we should get 500 divided by ln 0.6. No. Second ln of ln 0.6 divided by 100, and that's going to be times 100 equals, all right, so here we go. We're going to divide both sides by this whole thing. E to the ln of 0.6 divided by 100 times 100 divided by ln of 0.6 divided by 100 times 100. Oh, that's E, sorry. So A naught is going to be equal to okay, so you can see that here I took 500 divided by, and I put, because this is just an E term, this whole thing was one thing because the exponent was this whole deal here. I didn't need to put this in parentheses because this entire quantity was the exponent. If this would have been multiplied times something else, then I would have had to have put the denominator in parentheses, but I didn't need to. So this is 833.33. So the initial amount of the substance present was 833.33. All right, that was a long lesson. I know it was complicated, but at least we did have some experience doing it last year in Algebra 2. That's the last lesson for this week. Thank you. Have a great day.